So today, I'll be talking about deep distributed decision trees on Apache Spark. Specifically, I'll be talking about a package that we released called Yggdrasil. This work was part of an academic research project. It spanned numerous universities. Here are all my collaborators. We presented this work last NIPS. NIPS is actually coming up in about like 3 or 4 weeks in SoCal. But we presented this in Barcelona 2016. So who's all familiar with decision trees? Let me get a show of hands. Sweet, awesome. I didn't include any background, and it looks like I don't need to. So we all know that deep decision trees themselves are really good for a lot of different kinds of machine learning problems. They're highly interpretable, easy to train, easy to tune, and you can just plop one out, show it to a business user, and ask, does this make sense? However, scaling them is a whole different story. As the dataset size, which I'm going to denote n throughout this talk, grows, or as the dimensionality p grows, we see a lot of different scaling issues, such as the data not fitting on a single machine, or as the decision tree depth d gets really large, we see an exponential number of leaves. So the question that we're going to answer during this talk is, how do we train deep decision trees on a distributed computing environment? The most common approach is known as Planet. It's what's currently implemented in Spark. So if you call the random forest a classification, random forest regression, this is the algorithm that will be run. The data doesn't fit on a single machine, so we take every individual instance, here denoted by a row, and we partition them across our cluster. And then on each worker, they have a subset of data on which they try out all the different possible candidate splits. A candidate split is good if it results in more purity, so all the +1 labels going to one side, -1 label going to the other side. And then once this computation is done on all of the subsets, it's aggregated back onto the master, so the master can figure out how well did this candidate split do on my entire data set. There's some problems with this approach, however. Namely, if I want to compute all possible candidate splits for all possible candidate features, then that requires n times p, where n is the number of p is the number of features, and times the number of partitions, number of round trips. And furthermore, if your features are continuous, so they're not categorical, then there are like L-1, so in between every 2 data points you could split. And so that results in a lot of communication problems. And this is actually what the authors of Planet cited in their paper. It's a little bit hard to read, but it says, Planet makes a trade-off between finding the perfect splits for an ordered attribute and simple data partitioning. And in particular, prior to tree reduction, we run a MapReduce and compute approximate equidepth histograms for every ordered attribute. Why do they do that? Well, it's the problem that we were talking about with a continuous feature. If you have n different data points and it's continuous, there's n-1 possible spots you could split on. And so you're basically shoveling the data set back and forth between your master and your worker on every possible candidate split. And so the heuristic proposed by Planet is, let's compute histograms, and instead of trying to compute every possible candidate split, let's just consider b of them, where b is much, much less than n. This saves us on communication, but the trade-off is, if b isn't one of the best splits, we're never going to find the best split because we never consider it. There's some other problems with Planet, however. With this introduction of the b parameter, you have yet another knob you can fiddle with on your machine learning model. You have a trade-off between finding the optimal split as well as the communication cost and the runtime efficiency of the algorithm. And finally, we'll see in the asymptotics that as the dimensionality p or as the dataset d gets large, or the depth of the tree d gets large, we're going to see really poor runtime even when the optimal b split number of bins is chosen. Here's our proposed approach, and it's actually not too hard. The only difference, well, there's a couple differences, but the key distinction to note is rather than partitioning by row, we're partitioning by column. So we're not partitioning individual instances, we're partitioning individual features. This is reminiscent of columnar databases, and it's kind of where we stole the idea from. Rather than having each worker compute the sufficient statistics, how well did this split do on their subset of data, since a split only involves a single feature, they compute all the possible splits for a feature, and they figure out the single best candidate split for that feature aggregating back to the master what are the best splits for this feature subset that each worker is responsible on. Notice here, there's no more approximate binning. We don't have this parameter b because it doesn't matter that we consider all possible candidate splits. It's also equivalent to a serial algorithm on a single machine. We don't have to implement any form of locking to ensure that the entire data set has been processed and we can now start actually aggregating the summary statistics. You can take this and write a serialized linear execution for every possible parallel execution of this algorithm. The way that we do the column partitioning is extremely simple. In our Spark package, there's a method called row to column store dense, and an equivalent one for sparse datasets called row to column store sparse. All it does is it takes your RDD of a vector, so your rows, and it transposes them. Note, however, this is actually a very expensive computation. It requires reshuffling of all of your data set. And so if you were to factor this into the entire algorithm's runtime, it wouldn't be too efficient. But you'll see that many data sets are oftentimes just stored in columnar formats for easy aggregation, easy analytics use cases. So here's an animation of how Yggdrasil looks. We start by taking all of our features. Suppose we have year built, square footage, price per square foot. And then we partition them across. Ooh, this is kind of messed up. OK, that's unfortunate. What you would have saw was you would have seen these features partitioned. So half of them would go to worker 1, half of them would go to worker 2. And then the workers sort each of the features by their value. So now all the features we've shown here are in sorted value. And we've colored their labels with green and blue. And now we compute the best split for each feature. This is super duper easy. All you do is you start on the left-hand side, you slide that threshold to the right, updating some summary statistics each time. And then at the end, you go over all the things you considered, and you pick the best one. You pick the best feature and the best feature split. You send that back to the master. And then the master selects from amongst all of the responses returned by the worker the single best feature to split on for this iteration of the algorithm. So let's look at these two things side by side. On the left here, you got planet. You got partitioning by data instance. And on the right here, you got Yggdrasil. You have partitioning by feature. The algorithms are very, very similar. The only distinction is instead of sending back summary statistics here, you're sending back the single best split that I already computed on this worker. And instead of computing the split here that gives you the highest purity or information gain, over here, you're just picking the best split because all you're sending back is the best split. There's less hyperparameters. You no longer need approximate binning to deal with communication. The communication cost is very similar. You're missing this constant right here. But this 2 to the d is inevitable because that's the size of the tree you're shoving back and forth across the network. And you're picking up this interesting term right here, which may be alarming at first. Notice that n all of a sudden showed up in our communication cost. Are we now communicating the entire data set? That's not very scalable. We'll answer that in a later slide. And finally, rather than considering only b possible splits, we're considering every possible split. So we're guaranteed to find the optimal split for each feature. And now, if you take these asymptotics and you start showing regimes on which dominates the other, you'll see that for high dimensional data, as well as for like very, very deep trees, Yggdrasil has better asymptotic runtimes than the planet approach. But this isn't news. Like I said, we still column partitioning from the databases literature, and column-based partitioning has been done many times in the past. How did we get this published in NIPS? This was another paper published last year in 2016, and they say that this process of partitioning by column is very communicationally efficient. However, the repartitioning of the data will induce a very high communication cost. And the reason why that's the case is because after you've done a split, the nodes have either gone left or right. And so now in those two leaf nodes, if you wanted to do another split, you should only consider the subset of the data that went into that leaf node. So not only do you need to you do need to communicate the path that each data instance took down your tree. And that's the origin of the n term in our communication cost. The way that we mitigate this problem is by being very efficient in our communication there. So I've highlighted in green the key distinction that we use to mitigate this cost and keep it minimal. Specifically, rather than sending around each node's entire split path, we send around a bit vector from each of the workers back to the master. The bit vector is a 1 if the node went to the right on that split, and a 0 if if that instance went to the left on that split. The animation isn't there. Oh, there's the bit vector. And then afterwards, the master will select the single best split out of all of them, compute this bit vector for the entire data set, and then send it back to the workers. So now that each worker will know, OK, the data that I have on all the data that I have, it's split like this now after this next iteration of the algorithm. And then finally, this last part. Workers sort each feature by bit vector, then by value. So when you're in the next iteration and you only want to consider splitting on the nodes that went left, by sorting on the bit vector, notice that now we have 2 ascending sequences rather than 1. I think this says price, but you see there's an ascending sequence here corresponding to the sorted left subtree, and then an ascending sequence here corresponding to the sorted right subtree. When you're choosing the candidate split, you should consider the information gain on this side and this side independently, because those nodes won't fall into the same branch of the tree when your algorithm is run. Here's the code that is the entirety of what I just described. You have a transposition phase, or you don't need to do that if you use a column or data store. For each iteration, you compute the best splits and gains. This is done in a parallel manner on each of the worker instances. These best splits and their information gains are then aggregated back to the master along with the splitting information. So the aggregate bit vector, the bit vector of the 0s and 1s, which direction each node went. Once this is aggregated, we then update the partitions with the best split that we found so that the next iteration of the algorithm can continue forwards. And we do this until a fixed number of depth d, where after that you say the tree's too deep, you don't want to train anymore. Why do we do this sorting? Well, because of the splitting, we have to keep track of the splitting trajectory of each of the training instances. If we were to instead just copy, then we'd have a copy into a new column after every split rather than doing the sorting on our existing data set. We'd have an exponential increase in the memory utilization. It would be exponential to the depth or the number of training iterations. Instead, when you sort, you're reusing your existing memory, and so the footprint of your memory is constant. Furthermore, computing the best split only requires a single scan, and most importantly, sorting based on the bit vector is big O of n, rather than big O of n log n, as you might expect. This is a little bit surprising. And to see why this is the case, it's important to remember, in the previous iteration of the algorithm, we have already either sorted by the feature value, or sorted first by the feature value, or sorted first by that bit vector, and then by the feature value. So we can actually leverage the ordering that we got from the prior iteration of the algorithm to sort the next iteration of the algorithm in linear time. The way this works is for every single one of the nodes in the tree, what I'm going to do is I'm going to get the range that that node of that tree is responsible for. And then I'm going to iterate over it. And I'm going to grab the bit, so whether it's split left or right, from the aggregate bit vector. And if it's a left, I copy it into a temporary array for the left. If it's a right, I copy it into a temporary array on the right. And at the very end, I just merge them together. It's kind of like merge. It's almost analogous to merge sort, but going the other way. Some other additional optimizations we do is sparse bit vectors. Because the bit vectors are 0s and 1s, and if your data set's balanced, you would expect that to be about roughly a half. You have 50% sparsity, and so compressed run length encoding can help you pretty far. We can also encode the labels. And finally, we can compress the feature columns. So we can apply schemes such as delta encoding or run length encoding on the features themselves. This is another idea we stole from databases, the ability to train, to do analytics on compressed data. Specifically, in the pre-processing of our algorithm, we modify it now to sort on the values in the column as before, and then to compress it, and then never decompress it, but rather to continue operating on this compressed column representation. Why can we do that? Well, Recall, we already need to sort the features. So after sorting the features, you start getting these runs if you have repeated values of any individual feature. And then these feature values are visited in sequential order when determining the best split. Remember when I said we start on the very left for the threshold, and then we just kind of march that forwards to the right, computing the information gains for each split? This kind of sequential traversal pattern is precisely the reason why we can stay using run length encoding of the feature columns. The downside, however, is after run length encoding, you can't just shuffle up the intermediate values the way that we had our little linear time sorting trick could. And so you'll have to maintain additional space to keep track of the splitting trajectories of each of the data instances. But the upside is immense cache locality. We'll see later that feature compression results in much smaller data sets that will fit on memory, no DRAM access, and that you'll see an overall improvement in runtime on a variety of data sets. So let's get into the results. How does this actually perform in the real world? So we benchmarked on the very popular MNIST 8 million, and compared to MLlib, when you're training a tree depth of 18 layers, Yggdrasil performs 6 times better than MLlib. We also tried XGBoost, but it was timing out on our Spark cluster after around 13 layers deep. We don't think XGBoost was for deep trees, actually, so that's reasonable. On a data set that Yahoo provided, which consisted of 2 million instances in a regression task, we see similar scaling as predicted by theory. When the tree depth gets large, MLlib's training time grows exponentially, whereas we see linear scaling with Yggdrasil's training time. There's a 24x increase when you're training trees of depth 18. And finally, we measured the communication cost, so the number of bytes sent across the network when running these two algorithms. And we see that in almost all training regimes, while the scalings are similar, in almost all training regimes, Yggdrasil is transferring less data as measured in bytes across the network. We also see that Yggdrasil is more scalable. When you have higher and higher dimensional data sets, and you bump the tree depth from 13 to 15, you'll notice that MLlib goes from this solid red line down here all the way up to that line up there. Whereas for Yggdrasil, it goes from this solid dotted purple line just up to that dotted red purple line. Yggdrasil is more scalable in terms of both the number of features as well as in the depth of the tree. And finally, those little nitty-gritty optimizations that made us different than columnar data stores, it actually does matter. You can see that we've dropped the performance in training time by over 40% just by applying these optimizations, and that each one adds on top of the previous one. It's available as a Spark package. It's already compatible with Spark 1.6. And if your code's already in Spark MLlib, all you got to do is change decision tree classifier to Yggdrasil classifier and remove this max bins parameter, because you don't need B. We're going to try all the splits. There's upcoming work to merge this into Spark 2.1. We're planning on adding features to let the algorithm choose automatically whether you want to run Yggdrasil or whether you want to run Planet. We're also looking to add approximate binning to further cut down our computation costs. And we're also adding support for when a single feature does not fit on a node. That's all I got for you. Thank you so much for your attention. Do you have any questions?
You never said anything about the quality of the model. I mean, you didn't say anything about the quality of the models. Is there any difference between these methods and the quality, precision, accuracy?
Yeah, that's correct. We didn't report any empirical results on the quality, and the reason being is if you have a 10-layer decision tree trained using the same rule, you would expect more or less the same tree modulo the binning. And so in our NIPS paper, we reported the results on quality, and we saw that the quality was more or less the same. However, for certain data sets, depth actually did matter on the quality, and so a tree of depth 5 trained a lot worse than a tree of, say, depth 12.